We are going to be continuing evaluating limits analytically, and in the last video what we came across was we recognized patterns where we could use direct substitution, and what we did find were there were certain things such as polynomials, radical functions, composition functions, and some rational functions that you could just use direct substitution with. And so we really played around with that idea and we practiced with those. Now what we're going to find is when you can't use direct substitution, when something goes wrong and you do not get a defined answer, we're going to have to manipulate. So substitution theorem, this is just straight out of the book. If f is a polynomial function, then you can always directly substitute. We found that. So basically what happens is whatever function that you're trying to find the limit of, you can end up taking that value that you're approaching with the x values and just directly substitute it into your function. So for a result of f of c. We also found that rational functions that are not undefined, you can directly substitute in composition functions and radical functions. So now here's the thing, we need to consider some rational functions, because if we do wind up with that 0 on the bottom, for example, let's say we got something like that and we did try to directly substitute. So we were saying this is a quotient, so sure, I can just go ahead and do the limit of x to the third minus 8 as x approaches 2 all over the limit as x approaches 2 of this function x minus 2. And then here is now on the bottom is where I'm going to focus. Here is now where you would say this is just a polynomial on the bottom. I could directly substitute in, but what do you get? You get 2 minus 2, which is 0. So regardless of what you got on top here, oh, it's actually 0. Regardless of what you got on top, what you have on bottom is this undefined. This is called an indeterminate answer, and you can't determine anything from it. So what we're going to need to do is manipulation. This lesson is all about manipulations. There are three various things that you can do. There's what I call divide out or factor. We're going to look at an example of that. We're also going to be able to rationalize or condense to one fraction if there's multiple fractions going on. So you're going to see an example of each one of those here in a little bit. So this number 37 is like the example that I just presented. So you always do want to try direct substitution because obviously that's a very direct, easy method. But what we'll see here is you can't do that. So garbage, right? So we're going to manipulate. What you're trying to basically do is you see this on the bottom, this x minus 2, that's what's giving us a problem. So reason with me. If I were to say, could I get that x minus 2 off the bottom, this is what you're going to kind of hope for. On the top, we have a higher degree polynomial, so you could kind of hope that, could I factor that? Could I factor that so that one of the factors is x minus 2? Because if that were the case, then this x minus 2 on the bottom would cancel out, right? They'd be gone. We call that a hole. So what you are going to ask yourself is, this problem right here, x minus 2 times what is equal to this x cubed minus 8. It's just as simple as 2 times x, 2 times what is equal to 8. So what you would do is you would divide, right? Divide top dog in the house. You would take 8 divided by 2 and you would solve your 4. The same thing is what we're going to be doing here. We're going to be saying, well, x cubed minus 8 divided by x minus 2 is equal to what? And so we have a synthetic division method, and we did do some algebra boot camp. So this is where that synthetic division is going to be coming in. So here is the factor. This right here on the outside of the synthetic box is going to be our root. So if you had a factor of x minus 2, then one of the roots or one of the zeros is going to be at x equals 2 when you add 2 to both sides, right? So here is one of our roots or one of our zeros, so I put that on the outside. Drop this down, multiply. We got our 2. Add those together. Remember with synthetic we add, multiply. We get 4. Add these together. We're going to get 4. 2 times 4 is going to be 8. Add those together, we get our 0. So remember, this is our remainder, and that's what we want. That last column that we set up is it's going to be a remainder. And also I need to keep in mind this right here is the polynomial up on top. We could have rewritten this 1x cubed plus 0x squared plus 0x to the first, but we don't typically write that, minus 8. And all of those coefficients need to be represented for each degree that you have here. All right, so we had to the third, to the second, to the first, and then to the 0. So all of our coefficients, that's why we had these placeholders 0 there. So then what this becomes is, this was a remainder. This is x to the 0, x to the first, x to the second. So in other words, we have x squared plus 2x, and then x to the 0, anything to the 0, remember, is just 1. So we have 4 times 1, so we just have plus 4. So this right here is that what that we were looking at. The x minus 2 times what? Well, times this polynomial, or this quadratic. So this is what we end up with. All right. And now what you can see is, instead of writing our limit, x cubed minus 8 all over x minus 2, I'm going to rewrite this in its factored form. This is what we just found with our synthetic division. And what can happen now is these cancel each other out. And that problem that was on the bottom is gone now. So this is a polynomial, and we can gladly just directly substitute now, and what we're going to get is 12. Now we have learned one way to manipulate by factoring or dividing out, and there's more. So the next way I'm going to teach you is what we call rationalizing, and if you ever see radicals, this is where you might be using this form of manipulation. Here is another problem that we're going to look at. So the first step is to always try direct substitution. Remember, if you can directly substitute in, that's great. You just go with that. So I'm going to try that. And I am just going to take whatever x I'm approaching, whatever value I'm approaching for x, and plug that into the function that we're analyzing. We're trying to figure out what's the behavior of our function doing as x is approaching 0, and we're going to try that using direct substitution. So you probably already see that there's a problem here, but I'm just going to write it anyway. Okay, so here we get that scenario of garbage again. Bad. So we are going to now try manipulation method number 2. This rationalizing, what we do in this case is you're going to see this pattern of a radical minus a radical, or it's a chunk minus a chunk, and there are radicals involved. And we are going to do that thing called rationalizing, and what that takes is multiplying that pattern by its conjugate. And as a reminder, what a conjugate is if you have this type of factor where you have an expression minus an expression, what you're going to do is multiply it by, it's almost exactly identical except for it takes on the opposite operation that's going on. So instead we're going to be multiplying by 2 plus x. Instead of subtraction, we're going to be adding the square root of 2. Alright, so the thing to take into account is what I've just done is I've changed this function by multiplying this additional piece onto the numerator. So in order to counter that, I'm going to also multiply it to the denominator, the very same thing. What you'll notice here is this piece right here where you have the very same expression on the numerator and the very same expression on the denominator. Anything over itself or anything divided by itself is always equal to 1. So all I've done now is I've taken my function times 1. This is just equal to 1. Alright, so I'm going to go off to the side here and now do some simplification, because on the top what we've done is we've taken this 2 plus x minus the square root of 2, and we have said we want to multiply it by its conjugate. This goes back to the fact that I have two factors and I need to therefore FOIL these. So this whole expression times this whole expression, oops, sorry, this needs to be addition. What I have to do is FOIL. So I'm going to take my fronts, my two front expressions, and multiply those. There we have the fronts, and then plus the outsides, so the two outsides, I'm going to multiply those. Okay, so there's that. And then plus the insides, I'm going to multiply the inside negative. If you needed to, you could change this into a plus minus. So we have plus negative square root of 2 times this 2 plus x square rooted. And then plus the lasts. Okay, and just for kicks, I'm going to change this into -1 out here, right? Because you can take any kind of negative number and just change it into -1 times that number to represent. Alright, so what we have is the square root of 2 plus x times the square root of 2 plus x. This would just become the square root of 2 plus x squared, because you have repetitive multiplication going on, so you can just turn that into a power. And these happen to cancel each other out. So what we have left in that front position is 2 plus x. And then we have plus. So now here is that magical piece of multiplying conjugates together. Those inner, this and this right here, those inner terms cancel each other out. And then I also have the lasts. I'm just going to focus on the square root of 2 times the square root of 2 again. So that right there is the square root of 2 squared. That square and power of 2 cancel each other out. So what we get is just -2. When we simplify that foiling out, what we just get, these 2's actually cancel each other out. We just get x. I'm going to start rewriting our function over here into an equivalent function that looks pretty much entirely different. That top, what we have determined, is just equal to x. Our numerator is just equal to x. And on the bottom, I also have a factor of x times, and it looks a little bit messy, that conjugate that we were forced to multiply onto the bottom. But here is what has happened. We had a problem with this x on the denominator, because when we directly substituted in that 0, we had a 0 in that denominator. But what we have done, and what you will see oftentimes when you are doing this rationalizing method, is you're going to get some sort of factor that may cancel that problem factor out. So I'm going to x out those. When you have x over x, it just turns into 1. What we get is an equivalent function, the limit as x approaches 0 of 1 over the square root of 2 plus x plus the square root of 2. And just a reminder, after all of this, I want you to bring this back, that this expression right here, this function, is equivalent to what we started out with. Right? If you were to graph this on your graphing calculator and you were to graph this on your graphing calculator, these two functions will look identical, except for the fact that we have a hole at x equals 0, right? Because that is that factor that we had in common on top and bottom, and we have a hole at that x value 0. So now what I'm going to try is direct substitution. Can I now directly substitute in? We're going to take this new function, plug in our 0. What we get is the square root of 2 plus the square root of 2. Right? And all of this is going to be equal to 1 over 2 times the square root of 2. And be completely proper about this, we don't like radicals on the bottom, so we are going to multiply the top and the bottom by the square root of 2 over 2. The same type of method that we did up here, you got to do to the top and the bottom. This is just going to be 2 times, and then the square root of 2 times the square root of 2 is just 2. So we're going to get 2 times 2 on the bottom, 4, and then on the top the square root of 2. This approximately is equal to 0.35. So we have just found the limit. What this graph is doing in y values, it's approaching 0.35 approximately as x approaches 0. Here is the graph of our function. I did this online, so you can't really see that there is in fact a hole there, but there is a hole. If you were to try the direct substitution, once again you would have gotten that undefined there, because there is nothing happening there. That's not part of the domain, because it produces an error as an answer. So what we need to always keep in mind is the definition of the limit, and what we're trying to do is look at this function, observe it, and try to figure out what's happening at around x equals 0 from both sides. So what you can see here, remember our approximate answer was about 0.35. So you can see here that's what was happening. These y values were approaching, in terms of y, 0.35 as our x values were approaching 0. So now we have accomplished the manipulations of factoring or dividing out. and then rationalizing when we're dealing with radicals. And the last one that we have to deal with is condensing multiple fractions. So this last one, I'm running out of time, so I'm going to be pretty quick with this. This is another boot camp thing that we looked at, but if you see multiple fractions going on, you have fraction minus a fraction divided by another technically fraction. So a lot of fractions going on, we're going to just have to perform the operations on fractions. So don't forget to resort to direct substitution, but I hope you see that when we substitute in zeros for our x's, we are just going to be getting that indeterminate form 0 over 0. Garbage. So I am going to start condensing this using our mad algebra skills. I'm going to rewrite this function. I first need a common denominator, so I have 1 over 2 plus x minus 1/2, and basically I'm just going to take the two denominators that I have and multiply them together. So my least common denominator is going to just be when I multiply my two denominators. So what I'm aiming to get is my denominators to be this, so I'm going to have to multiply 2 to the bottom here, which means I am also going to have to multiply 2 on the top. So 2 over 2 is just 1, of course, so I've not changed this because all I did was I took that term and multiplied it by 1. Same thing over here. I want to achieve that common denominator, which means I'm going to have to multiply to the top and bottom 2 plus x. Okay. So this is what I have so far. So I am going to simplify what I have on top. I'm going to get, okay, so this is equal to, now because I have a common denominator, I can go ahead and subtract these two fractions. So I'm going to get 2 minus and then 2 plus x, and I am going to keep that as a group because that is going to be important that I distribute that subtraction. So all over 2, all over that common denominator, and then I have it all over x. And I wrote up here over 1, that's going to help us in a little bit here. So you can simplify this, just don't let algebra get you. Oh, that algebra. Take that subtraction sign and distribute it. So we're going to get 2 minus 2, which is just going to be 0, and then minus x. So if you need to, go ahead and say this is plus, and then negate those two things. These are going to cancel each other out, but you're going to get negative x on top, all over 2 times 2 plus x, all over x over 1. Alright, so finally, here is now where I have a fraction going on divided by a fraction. So that's kind of why I wrote that x over 1. So whenever you're dividing fractions by another fraction, why not just turn it into multiplication of the reciprocal? So we have negative x all over 2 times 2 plus x. Instead of dividing it by x over 1, I'm going to multiply it by the reciprocal of that divisor, which is going to be just taking that and flipping it. What I get in the end, these x's, I mean, you can rewrite this as negative x because negative x times 1, you just multiply straight across the tops for multiplication of fractions, multiply straight across the bottom times x. Oops, I kind of ran out of room. And here's where I'm going to rewrite this as negative 1 times x because that's the same thing. And those x's, there they cancel each other out. X over x is just equal to 1 over 1. So my rewrite is going to be limit as x approaches 0 of this new function. It's not new, I should say, actually. It's exactly the same thing as this, except for we've gotten rid of that hole that is occurring. So we have negative 1 and then over 2 times 2 plus x. And I'm not even going to finish this off. I want you to evaluate this. If you have any questions, you're going to let me know. So there's your homework set. I would like you to try those. This is a continuation of 3.3. Good luck.